Thank you. So yeah, um, I've been working on with Rust for side projects, and it's an honor and a pleasure to be able to speak at this Rust meetup. Thank you for inviting me. So today I would like to share a very crucial and important feature of Rust, which is, well, you know it already, it's traits. This talk is mainly aimed at Rust beginners with a background in programming, usually with object-oriented languages such as C++, Java, or C#. I'll be mainly talking about Java and C++ as comparison to Rust, but of course that applies to many object-oriented languages. So let's have a look at how we can avoid relying on inheritance, because not everyone has a rich uncle who can conveniently die and leave you a lot of money. How do you get by without inheritance, and how does Rust do it? And yeah, let's dive in. So there are different approaches to the same problem. The core problem that we have is that we want to write generic code. So let's say that we want to manipulate animals, and all animals, at least those that we want to manipulate, make a sound. So if it's a dog, we want it to bark. Otherwise, if it's a cat, we want it to meow. Otherwise, if it's a snake, we want it to hiss, and so on. So we could write code like this: if dog, then bark; else if cat, then meow. But that's very repetitive. You have to list it everywhere that you want them to make a sound. And whenever you add a new type, then suddenly you have to change every call site, because every call site has to handle the new animal. And also, like, if you want to take an animal as parameter or store it in a collection or return it, what is the type of a dog or a cat or a snake or and so on? So you could model that with an enum in Rust, but that's not what we're here to talk about. So let's have a look at how Java does it. So Java, usually you would write an abstract class animal, and you would define a function cry that is what animals do. And then you can create a class cat that extends animal, that inherits from animal, and then implement that function cry. You don't have to do it through an abstract class. You could do it through a concrete class, even though it's usually bad style, or you can do it through an interface, which is a bit like an abstract class, except that it cannot have fields. So to summarize, in Java, you can only inherit from a single class, but you can implement multiple interfaces. The interfaces cannot contain fields, but the classes can. And the interfaces can provide a default implementation for some functions. Okay, now let's have a look at how C++ does it. So this is, again, things that most people know. I'm just laying the ground for what we're going to compare it against. So in C++, you would do a similar thing to Java. You would have a class animal that has a virtual method that is not implemented here. That's the equals 0. And it's abstract only because it has an equals 0 method. And then you would write a class cat that inherits from animal and override the method cry to say when a cat cries, it goes meow. So the thing is, in C++, you do not have a clear boundary between a class, an abstract class, and an interface. So in order to implement multiple interfaces, you have to have multiple inheritance. Again, because there's no boundary between a class, an abstract class, and an interface. An abstract class is only abstract because it has a function that is not implemented, and an interface is a Java concept that doesn't really translate to C++. So with multiple inheritance, you can even have trouble with a diamond inheritance, where you inherit from two classes that both inherit from the same. So from which path do you get your inheritance from the top one? It can be complex. So that's why people usually recommend composition over inheritance. but that doesn't always work. It has, I mean, there are some drawbacks. Another way that C++ writes generic code is with templates. So, for instance, here we have a function makeItCry that takes an animal and calls animal.cry. However, here I wrote type name animal, but I could have written type name t and then take a const tref, because it doesn't, the name animal doesn't mean anything there. It's just a name for the type, and we don't have a way to restrict to the interface animal. And actually, you could pass something that's not an animal, but as long as it has the cry method, it would work. So this is what we call duck typing. If it quacks, it's a duck. If it cries, it's an animal. And we don't really know if it's actually what we meant by an animal, but this is how templates work. There's no interface declaration. It's going to come in C++20 with concepts, but it's not there yet. And then there's so the templates are doing monomorphization, so meaning they copy paste the function for every type that it's used with, and then inline the type, which makes a different function for every type. There's no one function that handles every type. It's just a copy of that function. Okay, now that the context is set, let's have a look at how Rust does it. So for Rust, we have traits. So a trait, for instance, we can introduce the trait animal that has a function cry. And then if we want to implement a cat, then we declare the cat. This is a struct. It has fields or not, doesn't matter. And then separately from the declaration of the trait and the struct, we say that cat implements animal. So we implement animal for the cat type. And since animal requires you to explicitly define the method cry, we have to say, well, cry for cat does this. So another example, if we have a struct dog that has a name, then if we implement animal for dog, then we can have a different implementation. Say, my name is, Woof. And then that's how a dog will cry. In summary, a Rust trait declares an interface. It's decoupled from the type declaration and from the trait declaration. A type can implement multiple traits. And traits don't have fields. They can only have methods. So it's a little bit like Java interfaces, except that they are used both statically and dynamically. We'll get a bit more into that right now. So how are they used dynamically? For instance, if you want to write the makeItCry in Rust, you would say, I take a pointer, like a reference, to an animal. But since animal is not a concrete type, you have to say to a dynamic type that implements animal. So that's what the little din keyword, let me point it, that's what the little din keyword means. And then you can use animal.cry, and because it's a method of animal. And here you only know that it implements the type animal, the trait animal, so you can only use methods of the trait animal. So like in C++, you cannot receive the animal by value because animal is not a concrete type, so you cannot copy it, or you cannot move it. You can just receive it by where it's defined somewhere else. So it has to be by reference or mutable reference or in a box or something like this. In Java, we don't have this problem because every object is a pointer anyway, so we pass pointers everywhere. Okay, now what if I want to return an animal? Let's say I have a barn and inside that barn there are animals, and I just want to get the first animal. So we have our function get barn animal that takes a barn and return an animal from the barn. So once again, you can see that we're returning a reference to a din animal, meaning we're returning a reference to something that we know implements the trait animal, but that's all we know. I left some blanks in the function definition because if you've played with Rust a little bit, you've ran into this lifetimes. I just wanted to say that here the lifetimes are also relevant because it's a reference that we're taking and returning. So here we're constraining implicitly the lifetime of the return animal to the lifetime of the barn. And yeah, so as in taking arguments, you cannot return a value of an animal. You have to return a reference or a box. Now, what if we want to do static dispatch? So static dispatch is when we know at compile time that we're what is the type that we're manipulating. So for instance, here we're gonna call make it cry on a specific animal. So here T is the type of the animal. We don't know what type it is, but we know for sure it's one concrete specific animal, and we know that it implements the trait animal because we wrote it here. And since we know that it's an animal, we know that we can call cry on it. We cannot access any other methods of T like we would be able to in C++ because we are limited to what the interface animal says. So we can only use methods of the trait. And this is like C++ templates, this is monomorphization. So we're going to make a copy of that function for every animal. So there's going to be make it cry that takes a cat, make it cry that takes a dog, make it cry that takes something else. And here we can take the animal by value because we know the exact type, it's T. So, and make it cry that takes a cat, we know that it's a cat. So we can take a cat by value, we know the type. And yeah, in C++, you can do duck typing and use pretty much anything. So if we want to return an animal, well, it's the same. If we want to, we can return by value, it's okay because we know the type of the animal is the T. So you can return by value. Usually when you do static code, the errors are clear because you know the exact types that are involved. The code is usually faster because instead of having to jump through pointer-to functions, the compiler can optimize and inline the functions. But that could also lead to code bloat because you're copy-pasting the same function for every type that you use it with. So it has its downsides too. But usually it's better to do static dispatch if you can. That's not always possible. For instance, if you have a vector of animals, you cannot have a vector of, well, if you have different types of animals, then you have to store boxes or reference to them. So for static dispatch, you can have a constraint. You can have multiple constraints on the type. So for instance, you can say that T has to be an animal and a runner, so that you can use both cry and run. And you can either specify the constraint when you declare the type argument, or after declaring the function and the return type in the constraints below. It's just syntax, both are equivalent. So how are traits used in Rust? In everyday Rust, you will use some traits. I guarantee you. For instance, one trait that you will most likely use is egg and partial egg. So this is how Rust knows what you mean when you say A equals B. It's because there's an implementation of partial egg that compares the type A and B. So here I've copied a very simplified trait, partial egg. So it has one unimplemented method, which is egg. So for equal, it takes the object and another object of the same type and returns a Boolean, whether it's true or false. And it gives you for free the function NE, not equal, which is by default implemented as the opposite of egg, of equal. And there's some difference between partial egg and egg, being that partial egg can return false if you pass twice the same object, but an egg has to return true if you pass twice the same object. And we say that egg is inherits from partial egg if you want, as it has the added constraint that the type has to be partial egg, because it means that to be equal comparable, you have to be at least partially equal comparable. Let's not get too deep into that. It's not critical. So let's implement partial egg for a type. Let's say you have a struct URL and it has lots of fields, different ways to represent the same thing. So you want to say that two URLs are equivalent or equal if they have the same canonical representation. So you will implement partial egg for URL, saying, okay, I take a URL and another. So the self with a capital letter is the type for which we're implementing the trait, so URL, and then returning a Boolean true or false, and we're just going to compare the canonical representation of the two URLs. And that way, once you have written this, you can write everywhere URL A equals you can check if URL A equals URL B without calling .egg, because the compiler knows that you implemented partial egg, so it can unwrap the equal comparison. Now, I want to talk to you about my favorite trait in Rust, and it's the Iterator trait. But for this, I have to introduce the new concept of associated types. So associated types, they will look familiar to C++ template gurus. You want to say the iterator has a next function that returns an option of something, but the option of something, this type is part of the interface. So you have to say what is the type that you're going to return. So item is part of the interface, and when you implement iterator, you have to say what is item. So item, that can be a regular integer, or it can be a reference to a cat, or it can even be a dynamic reference to an animal. Anything goes. But when implementing iterator, you have to say what is the item in addition to implementing next. And iterator comes with many more functions that are defined in terms of next. So when you implement iterator, when you implement just next, you get lots of functionality for free. So let's write an iterator. It's going to be a simple one. It's okay. So we'll create the type always same, and it contains a value. Then we'll implement iterator for always same. Say that the item of the iterator is going to be an integer. And then whenever you call next, we'll just return that integer over and over and over again. So how can we use it? Well, we can create an always same, and this one I'm creating it with the value 1. So always same is going to be always 1. Then let's print with some debug, which by the way uses the debug trait. We'll take from always 1, we'll take the first 10 items. Because we implemented it so that it never returns none, it's an infinite iterator, so we cannot just say, put everything in a vector. We'll take the first 10 and put that into a vector. We'll collect them, put them into a vector. So when we print this, it gives us 1, 1, 1, 1, 1, 1, 1, and so on. You'll notice that I didn't define the take method for always same. I didn't have to. It's a method from Iterator that is defined in terms of next. It just calls next 10 times. So it returns an iterator, it returns a new iterator that will stop after 10 times. Okay, now let's say that we're receiving a vector of data, vector of integer, and we want to return an iterator that takes only those small numbers, those are inferior to 3, and it will infinitely loop over them for some reason. My problem is that I cannot write, I don't know what to write for the return type. Okay, let's have a look at, let's cut it down and see what we can do. So the iter method on vector returns an std slice iter with item equals I32 because, well, here it's integer because it's a vector of integer. In general, it returns an item the same as the vector, what the vector contains. Then we call .filter, which wraps that iterator into a new iterator of type std iter filter. Then we call cycle, which wraps that one into another iterator called cycle. So as a result, the return type of the function should be something along the lines of it's a cycle of a filter of a slice iterator of pointer to animals, sorry, of integers. I should correct the slide. And then some closure. What is that some closure? Well, if you look back at the type and the filter, it had a closure to check that the numbers were small. And the closure has a specific type because it can do some captures, and this type we cannot write. That's a problem because how do I write my function then? In that case, you can just say it returns some concrete type, unspecified, but what we know about that concrete type is that it implements the type iterator with that specific item. However, this is still a placeholder for a single concrete type. You cannot return two different types just because they both implement iterator. Otherwise, you would have to return them by reference to a dynamic object that implements iterator. Here, it's all static, so there's no vtable involved or anything. It's just a convenience function to say that yes, the type that we're returning, we don't know how to write it, but it implements iterator. So a question that I often see beginners ask is, why can't I print a vector? Well, vect doesn't implement display. It's a trait. It implements debug, but it doesn't implement display. Well, in that case, I'll just implement it. Well, you can't. Why can't you implement it yourself? Well, if everybody could implement vector themselves, then you could have several implementations that would both be valid, and that would lead to chaos and ruin the utter collapse of civilization. Since we don't want that, Rust has a defense mechanism, and that defense mechanism is the orphan rule. So the orphan rule states that you can only implement a trait for a type if you either define the trait in your crate or you define the type in your crate. So it means that you have, when you want to implement a trait for a type, you have to own at least one of the two, or both. So you can implement standard traits for your types. For instance, we implemented the standard Iterator trait. Or you can implement your own trait for standard types. You can add methods to vector. But you cannot implement standard traits for standard types. So you cannot implement a trait introduced in another crate for a type introduced in another crate. Okay, is everyone still following? We'll move on to advanced traits. So those are things that you will usually not want to do in your code, but you should know that it exists in case you need it, and it turns out to be the best implementation. So, for instance, you could do some downcasting, which is instance of in Java or dynamic cast in C++. Usually not something that you want to do. It usually means that you don't have the right abstraction. It's possible to do in Rust if you add some boilerplate to the types and so on. It's a bit awkward. Some crates make it easier, but it's still not great. You have to change the definition of the trait. However, there's usually a way to reframe it so that you don't depend on downcasting. So let's say that you're getting an animal. So this is a Java example. You're receiving an animal. You're checking if it's a dog or a cat, then I want to adopt it. And if it's a mosquito, then I want to squash it. Well, so the techniques I'm about to show work also in Java. It's just that in Rust, I want to give you tools when you come around, along this problem to change the way you think and maybe reframe it in a way that is better suited for the tools that Rust gives you. So you could either extend the trait animal and add the function adoptable that by default is true, and then when you implement animal for mosquito, you say that adoptable returns false. Or you could create a new trait. You could say that things can be adoptable. By default, they are, and mosquitoes are not. But you still have to say that that cats are adoptable and dogs are adoptable, and for every animal, you still have to implement adoptable as well, in addition to animal. And your code would look like this. You take a T, and that T is both an animal and adoptable. Since it's both, you can check if it's adoptable. If it's adoptable, then you can pet it, which takes an animal. Otherwise, you can squash it. So some of the traits that I presented so far were you saw them, but you never actually implemented them yourself. For instance, debug, partial egg or egg, I doubt that you actually implemented them yourself. Usually, they have an obvious implementation, so you would just write, you just derive the implementation from the structure. That way, dog implements debug, partial egg, and egg with the obvious implementations. And usually when every field of a structure implements a trait, you can recursively implement it by calling it recursively on every field. And to generate this implementation with the derive macro, you can actually write your own derive macro for your own traits using procedural macros. I'm not going to get into that because that's a complex topic on its own. Another thing that we kind of touched on with partial egg and egg is operator overloading. To define what the plus does, you just have to implement the trait add for self and the right-hand side, which by default is self. And so we could implement add for cat, say that when we add two cats, it returns an integer, and when we add them, it returns actually two. You'll notice that I implemented it for reference of cat and not for cat itself. You could implement it for cat itself, but then you would have to move the value into the plus of the addition operation, and that might not be what you want. So For instance, here we're adding twice the same value, so we couldn't do that if it was by value. We had to do it by reference. I'll quickly skip over the deref trait because it's not super super important, but basically it's you can specify what it means to dereference a type. So for instance, when you have a man, you can dereference it into 2 kids, and hey, it's just 2 kids in a trench coat. And you can pass a man to a function that expects 2 kids because the compiler will just dereference it on its own. Okay, so auto traits are traits that contain, so some traits contain no interface and are used just as marker traits. For instance, we saw that ek, in addition to partial ek, was just used as a marker to say, oh, and those types have the strong equality constraint. Some marker traits are automatically implemented by the compiler. For instance, sized just means that we know at compile time the size in memory of your object. You can't make your own auto traits except if you're in Nightly and with some features, but maybe in the future you will be able to. There are some other auto traits that are interesting, like send and sync, but usually you don't have to think about them. So in conclusion, traits are quite different from C++ and Java. They resemble Java's interfaces or C++ abstract class with no fields, but it's not quite the same. Their power comes from the fact that the implementation for a type is separated from both the declaration of the type and the declaration of the trait. So many things in Rust are implemented as traits, and they're very crucial to writing idiomatic Rust. And a very nice advantage of traits is that they're used both dynamically and statically for specifying an interface. So it's the same mechanism for both compile time and runtime. Okay, are there any questions?
Hi, Valentin. Thank you for this presentation. It was very interesting. I did a little bit of work in traits, but I learned a lot of new things. Yes, there are questions, and if that's okay for you, I will relay them to you. Is that okay?
Yes.
Okay, there is one question actually in the organizer team. We asked ourselves, you showed traits in conjunction with structs only. Is it possible to define traits for other types like enums?
Yes, it's possible to define traits for any type, including for an integer. So you can add methods to integer by implementing a trait for them. And of course, it works for enum. You have to be careful whether you're implementing the trait for the enum entirely or for variants of the enum.
Okay, thank you. Thank you very much. The next question comes from Matthias. I will just read it to you. Will we ever get constant iterators, he asks. While and loop can already be used in const functions, but for does not yet work. I suppose that's also because it uses iterators which are not constant. Do you know more about that?
I don't know more about that question, sorry.
Okay. Okay, yeah. The second thing is also a longer question. I'm not sure if you have Discord open. It's in the meetups channel. Vladimir is asking, the only difference I know between generics syntax and associated types is that one cannot implement a trait with an associated type multiple times for a type. Are there any other differences? And he brings also an example.
So yes, that's one key concept of associated types. For instance, when you implement iterator for vector, it can only ever return one type. So you don't want to implement iterator of integer for vector and iterator of string for vector, because both don't make sense at the same time. So when you implement, actually you don't implement iterator for vector, but you implement iterator for the iterator type returned by vector, sorry. So if you had generics at the trait level, then you would be able to say iterator of integer for that vector of string, which doesn't make sense. So it's a good point to point out. I guess another key difference is that you can have default values for generics, but I'm not sure that's the case for associated types. I might be wrong. So it's mainly a question of what is the interface that you want to present. Do you want to present an interface that is variable on every trait, or do you want to present a single interface? It's just that you need an extra item, an extra type to be specified.
Okay, thank you very much. The next one is a short one. Christian asks, would it make sense to move all the logic into traits and let classes just hold fields?
Well,
or structs, of course.
Yeah. This is essentially what happens already, because when you add methods to a struct, then you say impl for struct. So you're already doing an implementation block that is separate from the data declaration of what the shape of the struct looks like. It's just that sometimes you want to have some functions that are limited only to a single struct, because it doesn't make sense to have another struct define them. And so you're, in a sense, you could say that you're implementing an anonymous trait just for that struct. So you're declaring that this struct implements an anonymous trait, and that the default impl block is the implementation of that anonymous trait and the interface at the same time.
I didn't look at from that point of view, but yeah, that's an interesting point of view. Yeah, thank you very much. The next one is another question, a short one. You mentioned the diamond problem. I think you mentioned it with C++.
Yeah.
The question is, can the kind of diamond problem also happen with traits?
So yes and no, because the thing is, your traits cannot override the methods of another trait. They're basically, traits are just here for the interface. So if you get the interface from two different traits, it's okay. What the problem in C++ is that in the diamond, the two classes in the middle can implement the class at the top in different ways. In Rust, you can have a diamond trait implementation, if you could say, except that it's not really a diamond. You don't, when a trait inherits from another, it just means that it requires the class that implements it to also implement the super trait. So ek doesn't inherit from partial ek in the way that if you were to somehow just implement ek, you don't get the .ek and .any methods. It's just that to implement ek, you have to implement partial ek. So if you had the same requirements from two traits, it's not a problem. You just have to implement the requirements and implement the two traits.
Yeah, that's clear. I think you described it very well. I could understand it, and I hope the question was answered with that. Let me quickly check whether we have something in the chat. No, I think that chat is empty, and meetups and technical discussion. Yeah, I think you answered all the question. Let me quickly ask the crowd where we have additional questions. This is your last chance to ask your questions live. While people are thinking about it, Valentin, will you be available for questions on the Discord server after your talk for another few minutes?
Sure.
Oh, awesome. Awesome.
I just want to say I'm coming back to the const iterator question.
Mm-hmm. Yeah.
So I don't know specifically about const, but something that I didn't mention about the iterator trait is that it's what powers the for loops. So when you say for a in vector, what happens behind is that there's an into iterator trait that turns the vector into an iterator, and then we iterate over that with the .next. And so all of that is just syntactic sugar provided over the iterator trait.
Thank you very much. Thank you for pointing that out. I would like to point out for people who are watching on YouTube, and I know there are some people watching on YouTube there, we don't use the discussion on YouTube. If you want to ask questions, please come to our Discord server and ask your questions there. We will relay them to our speakers. Valentin, I think we are through. I don't have any more open questions. Thank you very much for this great talk. I learned a lot, and I'm pretty sure that it was very interesting for many of our viewers. It was a pleasure having you here, and we hope that you also enjoyed giving this presentation here at the Rust Linz meetup.
Thank you for inviting me. It was very nice. It was my first time doing a presentation without seeing the audience, so that was interesting. But it was a great opportunity, and thank you very much.